Hello everybody, this is the second video clip for this chapter 5. Okay, we are still in the section 5.1. Previously, what we have learned is that if we are going to say that the limit of your function f of x as your x goes to c does not exist, okay, we are going to find a sequence xn in the set A except the point C, and this set A is actually the domain of the function f, okay, such that your xn goes to C, but the your f of xn, the limit does not exist. Okay, or if you can find two sequences xn and yn, which is again in the domain except that point C, such that both xn and yn goes to C, but your f of xn goes to L1, your f of yn goes to L2, which are not the same, then we can also conclude that the limit of the function at the particular point does not exist. So let us use these two criterion to go over some of the example over here. The first one, we look at the function f from the set of real number except the point 0 to a real number, which is defined by fx equals to x over the absolute value of x. Okay, so what does this mean? Actually, if your x is positive, then your absolute value of x, it is the x itself. If your x is negative, then the absolute value of x, it is a negative x. So it means that the first one, because your x is not 0, so it can be 1. If your x is positive, it will be a negative 1. If your x is negative, so it looks like the sign of the number, the real number x, okay, that is insert into that function, okay, and then this function just tell you what is the sign of this number. Okay, so this function is called a signum or a sign function, okay, and usually it is denoted by SGN. All right, and we would like to say that the limit as your x goes to 0, okay, of this function f of x does not exist. Okay, so how are we going to find this the sequence, okay, that it goes to 0 but your f of xn, I mean, does not exist or does not converge? Okay, for this one, because it is depends on the sign, so the sequence xn that you may think of should involve the sign as well. So you may think of your xn to be negative 1 raised to the power n over n, remember, and this one, it is of course go to 0 as your n goes to infinity. So this is the point C that under this consideration, right? So your xn goes to C. However, if you look at your f of xn, okay, it is again, as we told you, that it is depends on the sign. So your f of xn is actually negative 1 raised to the power n, right? Depends on this n, whether it is even or odd. Okay, it will be either 1 or negative 1. And this one does not converge, remember, from your sequence chapter. Okay, this one does not converge, or the limit does not exist. So it means that this limit as your x goes to 0 of the signum of f also does not exist. Okay, all right, and for this course, okay, we are not going to like not only looking at the function that you have learned before from the math one, but also like introduce some of the other function that you sometimes may encounter as you learn higher and higher in terms of mathematics and also in terms of economics. Okay, for example, we can think of this kind of function. Your function f from a real number to a real number is defined by a 1. Okay, if your x is rational, and it is 0 if your x is irrational. Okay, and this kind of function, the limit as your x goes to any real number, does not exist at all. Okay, does not exist at all. So however, to conclude this example, okay, we really need to bring up the old knowledge, okay, from before midterm, okay, so that if we let your c to be a real number, then we can find a sequence Rn, okay, which is a sequence of either rational, okay, number such that your Rn goes to that real number c, okay, as your n goes to infinity. On the same token, this Rn can be a sequence of all irrational, okay, number such that this Rn also goes to c. Okay, this one is by the density of the rational and the irrational, right? Okay, so for this one, we first letting your c to be any real number, and then we are going to prove the non-existence of the limit, right? And to do this, let us use the criterion, this one, that we are going to find the two sequences, okay, that goes to the same point c here that we let, but the function value of both sequence goes to some other places, okay, that are not the same. All right, so let us choose one sequence Rn which is all rational, okay, which we can choose, okay, such that this rational sequence goes to c, and choose another Sn which is all irrational, okay, such that all these irrational goes to c as well, okay. And since because your c is in R, so if to be exact, okay, we can say that this one we don't need the c itself, this one as well, because we don't even know whether your c is rational or irrational, okay. However, we can choose this kind of sequence, okay, that still goes to c, and also this sequence that also goes to that point c as a real number, okay. However, okay, the function value of Rn, okay, because your Rn, it is all rational, so it means that it will always what 1, okay, take a value 1, and then because of this is a constant sequence 1, so it goes to 1. And if you look at the function value of the sequence S of n, which is again irrational, so it take value 0, so it is a constant sequence, again the limit goes to 0, so they are not the same. It means that your limit as your x goes to c of your f of x, this function does not exist, okay. All right, so you may think of this kind of function and this kind of technique as well, okay, as you learn this course, okay. So let us elevate ourselves a little bit, okay, but it's not that difficult. This one actually you can pause the video and then try to do it by yourself first, okay. So we need to conclude two things. The first thing is that as your x goes to 0, your f of x, the limit of this function f of x exists. However, as your x go to some other places rather than 0, the limit of this function does not exist, okay. So you may say that, hey, let me start from the second assertion, because We already have seen the example from the previous one, right? So let us pick up each and every real number c, okay, rather than 0. All right, and then again choose your Rn, okay, which is in this rational except the c, and your Rn goes to that particular point c, and your Sn, which is in the irrational except this c, and your Sn goes to c as well. We can say that the f of this Rn, okay, it takes value because your Rn is all rational, so it takes value Rn, right, which is goes to c, and this one is not a 0. However, your f of Sn, which is irrational, so it takes value 0, which is goes to 0. So of course they are not the same. So it means that your limit as your x goes to this particular point c rather than 0 of this function does not exist. Okay. But if we want to try the first assertion to saying that the limit of this function as your x goes to 0 exists, okay, so let us do it by using the definition. Remember the definition, as your limit goes to c, okay, of f of x equals to L. So it means that for epsilon there will be a delta, and for x which is inside the domain, if your x and c, okay, the distance less than delta, then the distance between fx and L, okay, will be less than epsilon. So let us do it this way. So let us start by thinking that what should be this limit L, okay. So as your x goes to 0, okay, what will happen, okay, if your x is all rational, okay, then it will be the function value will be the x itself, right? Okay, so as your x approach 0, then it should goes to 0, right? And if your x is outside the rational, it is irrational, then the function value also 0. So we guess, okay, we take a guess that this one exists and it is 0. Okay, so that should be our L. So we start by letting the epsilon, okay, greater than 0 given, and we are going to choose the delta. Okay, however, we cannot choose at once. It depends on the calculation, it depends on the inequality that we are going to have. Okay, so and then after choosing the delta, let us get the x as any real number, because right now your a, the domain, is a real number r. Okay, and because your x is a real number, okay, it can be two ways, whether it is rational or irrational. However, before that, okay, this x is as a real number will satisfy the distance from the x and 0 will less than the delta that will be chosen. Okay, so this one you see is 0. Okay, so the first case that we can consider is that if your x is in the rational, okay, if your x is in the rational, then the inequality that we need is the f of x minus L, which is 0. However, your x is the rational, so your f of x is the x itself, which is, you see, this one and that condition, they are the same. Okay, and at the end we need it to less than epsilon, right? But right now from this condition we know that it is less than delta at once. Okay, what was another case? The second case is that if your x it is irrational, then it means that your fx minus 0, it is, I mean, as the irrational taking place, the function value always 0. So 0 minus 0 is 0. So it is, of course, I mean, the delta must be positive, right? So this one is also less than delta. But our goal is that the thing will be less than epsilon. So we can say that this delta can be the epsilon itself, okay? So that your fx and 0, I mean, in both cases, okay, the distance between them is less than epsilon. So from this definition, we can conclude that as your x goes to 0, your function will goes to 0 as well. This is the limit. Okay. So let us go over this last example for this clip. Okay, we have your function f from the real number to real number, which is defined by 2x plus 3 if your x is non-negative, and it is -1 as your x goes less than 0. We need to prove that this limit as your x goes to 0 of the function does not exist again. If you go back to your math one, you may using the right hand side and the left hand side limits, right? But this one we haven't introduced those things, so we need to use the thing that we have learned. Okay, so what should we do? So we again will pick up two sequences, that is go to 0 as your n goes to infinity, but the function value of these sequences, okay, are not the same. All right, so it means that one sequence should be a sequence of a non-negative number, another should be a sequence of the negative number, right? So we can, as I told you, we will always choose the easy one. For example, you can choose your xn to be 1 over n. Of course, it is positive, and your xn goes to 0 as your n goes to infinity. Okay, and your yn can be -2 over n, which is negative. Okay, and again your yn, I mean, you may say that y2, I mean, it can be 1, sorry, -1 over n. Again, your yn goes to 0 as well. However, f of xn, okay, because all the xn is positive, so this was 2 over n plus 3, which goes to 3, but f of yn, okay, it is -1 always, because they are, I mean, all the yns are negative, right? So this one goes to 1, goes to -1. Again, the limit of your f of xn and f of yn are not the same, so it means that the limit as your x goes to 0 of your f of x does not exist. Okay, now let us go over some of the theorem which will be the tools, okay, later on as we continue our study. This one, the first one, is saying that if your f is a function from the domain A to R, and your C is a cluster point, okay, don't forget that the cluster point is actually another name of the limit point of the A. If the limit of your function f of x as x goes to C is positive, okay, then we can find a delta neighborhood of the point C, okay, such that your function value is positive for all x inside this neighborhood. Okay, of course, I mean, the x that we talking about should be the one inside the domain as well. Okay, however, we can, you know, take away that point C, okay, but inside that neighborhood, except that A can be positive. All right, and of course, I mean, this this theorem can be proved if the limit of your function f of x is less than 0 as well. Okay. However, what we are going to prove is the positive part only, and the negative part will left as your exercise. Okay. So because it is the implication statement, so let us suppose that the limit as your x goes to c of the function, it is equals to L, okay, and the L is positive, okay, because the p is the limit is positive, right? Okay. So what does this mean? This means that for any epsilon, okay, that's given, for any epsilon that's given, okay, we can find the delta. Okay, so let us say choose epsilon to be something we still don't know. We can find the delta positive such that for all x inside A and your distance from C, okay, and x is less than delta, okay, then your function value and the L, the distance between them, is less than epsilon. Okay, so this is what we have whenever we choose. For example, if we choose epsilon equals to 1, then this one will be less than 1. Are we good? We will have that delta depends on the epsilon that we choose. Okay. However, we are going to choose the right epsilon so that our function value will be positive in the neighborhood of the C, okay, of the point C. If you look at this one, actually this statement is already create a neighborhood of the point C, okay, and also the one that is inside the A, okay, because right now if your x, satisfy this condition, so it means that your x, it is in A, right? Of course it's right here, and it is inside the C minus delta and C plus delta, right? And then because it is greater than 0, so it means that it take away already the point C, okay? So we already have your x in A intersection the neighborhood, the delta neighborhood of C, and then that x is not the C itself, okay? So we already have this statement. However, what we really need is that your f of x inside this set will be greater than 0. So let us calculate a little bit. This one, it means that your f of x minus L will be less than epsilon and greater than the negative epsilon. So it means that your f of x, it is less than your L plus epsilon and your L minus epsilon. But you need your f of x to be positive, right? Okay, so it means that this one, if we can conclude that this one is positive, then of course your fx is positive whenever your x satisfy this condition, is it? So you can just choose the epsilon that your L minus epsilon is positive. So it depends on your calculation. Okay, so the thing that you can easily think of is that your epsilon is L over 2 because your L is already there and your L is positive, so your epsilon is positive as well, right? And then if your epsilon is L over 2, then it means that your f of x will be greater than your L minus epsilon, which is L over 2, and it is also L over 2, which is again positive. So your f of x satisfy this condition. Sorry, your f of x, if your x satisfy this condition, the function value will be positive. Okay. If you say that, hey, I don't like L over 2, can we choose something else? Of course. Okay, L over 4 can do, or L over 10 can do, as long as your L minus that epsilon you're choosing is positive. That will do, right? So you really need to think of what if your f of x is, what if we need to prove that, if the limit is less than 0 and your f of x will be less than 0 inside that neighborhood. Okay, the next two, okay, that we have used, okay, and in math 1, and we also will be used later on, is that if we have the f and g, okay, as a function, and your c is a limit point of the domain of f and g, and the limit of f is L, the limit of g exists, and it is a real number m, then the limit of a function f plus g, it is simply L plus m. The limit of a function alpha f, it is simply alpha L, and the limit of f times g, it is simply L times m, and the limit of f over g, it is simply L over m, provided that your m is not 0, of course. Okay, so we are going to again using the sequential criterion or the sequential definition of the limit to help us solving this theorem. Okay, so we are going to let your xn to be any sequence, right? Because we talking about for all sequence in a rather than that point c, and your xn goes to c as your n goes to infinity, then of course the limit as your n goes to infinity of your f of xn, because it is equals to L, right? So it will be L, and the limit as your n goes to infinity of gxn, it will be m, because this one equals to m. And by the definition, if you talk about f and g xn, so it means that it is your f of xn plus g of xn. And if you're talking about a multiplication, this one is also a multiplication, right? If you talk about alpha f of xn, then it means that you have alpha times f of xn. Okay, and from the sequence we know that the limit can be separated, okay, by this operator, right? Okay, so it means that the limit of this one can be the limit of this function f alone and the function g alone, and then you just add them up or you just multiply them. Okay, however, for the last one, if your m is not 0, again your f over g of xn can be regarded as f of xn, g of xn, and then from the sequence chapter we know that all these can be separated. Okay, the limit can be calculated, separated, and then just take a division, okay, of these two limits together. All right, another thing that is the most important is the squeeze theorem. And again, the squeeze theorem, we are going to use the sequential definition of the limit, okay, by letting again your xn to be any sequence, right, of your a subtracted that point c, and your xn again goes to c. So by this condition, it means that the limit as your n goes to infinity of your f of xn is L, and the limit as your n goes to infinity of your h xn is also L, and your f of xn is less than or equals to g of xn, and it is less than or equals to h of xn, because right now your xn, it is an element of a subtracted at point c. So by the squeeze theorem of the sequence, we know that because the limit of this one and the limit of that one, I mean the left and the right goes to the same place L, so this one in between must be L as well. And because your xn is any sequence that goes to C, we can immediately conclude that as your x goes to C, your gx will goes to L as well. Okay, so that will be the another useful theorem, okay, that we may use later on. All right. So let us stop our video clip right here, and we finish section 5.1. We'll see you on section 5.2 next time. Bye bye.